we're going to continue our discussion of energy in Chapter 7. In the first video, we talked about work, power, and gravitational potential energy. Now I want to turn our attention to kinetic energy. That kinetic energy is energy that's due to motion. It has one thing in common with momentum in that kinetic energy also depends on mass and speed. However, our momentum formula, mass and speed, were equally important. The formula for kinetic energy is 1/2 mass times speed squared. In other words, speed squared means speed times speed. Or it's usually written 1/2 mv squared. Because it depends on the square of the velocity or the square of the speed, speed plays a much bigger factor. You can see if we were to double the speed, it would actually make the kinetic energy 4 times as large. If we were to make the speed 5 times as fast, it would actually make the kinetic energy 25 times greater because it goes as the square. So for example, if I have a mass that's 10 kilograms and it's traveling with a speed of, we'll make it simple, 10 meters per second, when I calculate the kinetic energy, it's 1/2 10, that's our mass, 10 kilograms, and then times 10 squared. That's going to be 5 times 100 is 500 joules. If I let that same mass have a speed of 20, if I double the speed, my new kinetic energy isn't double. Doubling the speed won't double it. It will come out to be, well, 20 squared is 400 times 5. It comes out to be 2,000 joules. So, in effect, if we doubled the speed, we'd have 4 times as much kinetic energy. Okay, that's going to lead us into our next big idea, and that's the work energy theorem. You'll remember in Chapter 6, we had the impulse momentum theorem, which stated that the impulse was equal to the change in momentum. Well, the work energy theorem says that the net work is equal to the change in kinetic energy. Now, remember what this word net means. That means the total work done on an object from all forces. If we use our definition of work being force times distance, another way we might say this is that it's the net force times the distance. That's going to give us our net work has to equal the change in kinetic energy. And usually the thing in kinetic energy that's going to change is going to be its speed. It's that 1/2 mv squared. Most of the time the mass itself is not going to change. Think about what this means in terms of an example. Suppose you push with 60 newtons to move a 50 kilogram sofa. Friction exerts a force of 60 newtons. I probably want to put that it's an opposing force. Remember, anytime we have friction, friction tends to oppose our motion. So we basically have a situation where we've got, here's this 50 kilogram sofa. You're pushing with 60 newtons. And friction is pushing back with 60 newtons. If somebody said, what's the change in the kinetic energy of the sofa? Well, we know that the work done, the net work, equals the change in kinetic energy. Well, net work, that's the net force times the distance, has to give us that change. In this case, what's the net force? Well, if you're pushing with 60 and friction opposes with 60, the net force is 0. It won't really matter whether you move it 1 meter or whether you move it 10 meters. When you're finished, the sofa will not have any more kinetic energy than it had when it began. This is a case where we say your push did positive work. You did do a force times a distance, but friction did negative work. So the total work done was 0 when you look at all of the work on the sofa. Okay. Net force is 0. Net force times distance tells us the net work done or the total work done is 0. So there's no change in kinetic energy in that example. Let's look at another example where there is a change or where there's something else to look at least. Suppose, for example, it says you slam on your brakes and the friction between the road and your tires and your brakes, there's a combined frictional force there, allows you to stop in 200 meters. So you slam on the brakes and the brakes and the friction apply some force I'm just going to call F. Now, interestingly enough, when you slam on your brakes, the force that you apply doesn't have anything to do with how fast you're going. If you slam them on with the full force that you can give it, that's the maximum force you can get from your brakes, whether or not you're going 5 miles an hour or whether you're going 75 miles an hour. So this force F tends to be a constant. The question wants to know is, if you were going twice as fast, how long would it take you to stop? Just think about that. If you were going twice as fast, well, we know that the total work or the net work force times the distance is equal to the change in kinetic energy. Okay. When we stop, we lose all of our kinetic energy. But think, if I'm going twice as fast, I have 4 times the kinetic energy. If I'm going twice as fast, I have 4 times the kinetic energy. If I want to change my kinetic energy to 0 and I have 4 times as much, I can't change this because that force my brake applies, that's as strong as they look. That's as strong a force as my brakes can apply. So what that means is it's going to take me 4 times longer. This distance is going, since this can't change, this is going to have to change. If this is 4 times bigger, it's going to take 4 times the distance. So the police understand this. That's one of the reasons at wrecks and things that they can look at skid marks, because if they can see what your stopping distance was, they can go backwards. They can work backwards from stopping distance, and they can calculate how fast you must have been going at the time of the accident. Okay. All right, let's talk about the law of conservation of energy. Simply stated, the law of conservation of energy says energy cannot be created or destroyed. That's a really important idea. But it seems like we use up energy all the time, but we don't. Energy can be transformed from one form into another form. Okay? The total amount of energy, however, is going to remain constant. One of the places that's really easy to see conservation of mechanical energy, now I have to be careful. If we're talking about the universe, energy is always conserved. You cannot create or destroy energy. If we're talking about conservation of mechanical energy, in some situations it's conserved and we have just as much mechanical energy at the beginning and at the end. In some problems, mechanical energy gets transformed into other forms of energy, like thermal energy or heat in particular. Let's look at an example, though, where mechanical energy is conserved. One of those places where it's conserved is if we're talking about something being acted on by gravity or in free fall. The gravitational force is what we call a conservative force, and gravity does not convert mechanical energy into heat or other things. Gravity keeps mechanical energy mechanical. We want to look at conservation of mechanical energy. One of the best examples is to look at something as it falls. Suppose that we have something and it's at a height of 20 meters. And we'll just let it be a 1 kilogram mass. So there's a 1 kilogram mass at a height of 20 meters. Here's the ground. At the beginning, when it's up there, maybe it's up at the top of a ledge or something, but we're going to let it fall off here in just a minute. It's sitting out there poised. If it's at rest, then I can stop and I can actually make a table of How much potential energy does it have? How much mechanical energy does it have? What is my total energy? So, let's have one more column. Put it at the beginning. Call that column H for height. When, right now at the beginning of this problem, the height is 20 meters, the gravitational potential energy, we calculate gravitational potential energy as mgh. So we've got a mass of 1, g is 10, and h is 20. Well, if I multiply 1 kilogram times 10 meters per second squared times a height of 20, I find that the gravitational potential energy is 200 joules. The kinetic energy is 0. Why is the kinetic energy 0? Because it's at rest. If something's not moving, its speed is 0, 1/2 mv squared, we know it's going to be at rest, so that's 0. That means my total mechanical energy is 200 joules. All I have to do to get mechanical energy is add these two together. And I know that the entire time that it is falling, the total energy is constant. We can't create energy, we can't destroy it, and when gravity acts on an object, it does not cause it to lose any mechanical energy. So we'll let it fall. Suppose it falls 5 meters, and so now it's 15 meters high. At 15 meters, I do the same thing. The mass is 1, g is 10. I see that I have 150 joules of gravitational potential energy when it's fallen right here. It's fallen to 15. I know that the total mechanical energy cannot change. This still has to be 200 joules. So where is the other 50 joules? Well, the other 50 joules is kinetic now. Think about what happens if I drop this red marker. At the beginning, it has no kinetic energy, but it's got potential. As it falls, it's going to gain kinetic energy, going faster and faster, and lose potential. All of the potential energy is getting converted into kinetic. When it's fallen, so that's only at 10 meters, well, if I do 1 times 10 times 10, I realize I have 100 joules. This is still 200 joules. So my kinetic is now 100. Notice that's the halfway down. At the top, all of the energy was potential. When you're halfway down, half the energy is potential, half is kinetic. If we fall another 5 meters, this is only going to be 50 joules. By this point, it's going very quickly, and we have 150 joules of kinetic for a total of 200 joules. And finally, let's talk about what happened right before it stops. If this is the ground and this is dropping, I don't mean after it stops. I mean just before it stops. So we're gonna just say a hair's width above 0. So close to 0 that 0 is a good answer, but it hasn't actually stopped yet. That has a gravitational potential energy of 0. All of the energy is kinetic for a total of 200 joules. Now, we can't create or destroy energy, but when you drop something and it hits the ground, it does stop. And at the moment that it's sitting on the ground, all the way on the ground, it doesn't have kinetic energy and it doesn't have gravitational potential energy. Once it hits the ground, we no longer have conservation of mechanical energy. We do still have conservation of energy. All of the mechanical energy, when it hits the ground, gets converted into another form. most of it gets converted into thermal energy. When you drop something and it hits the ground, the object that you drop, all the molecules vibrate a little faster after it slams into it. It literally heats up a tiny bit. Same thing for the ground below. It also heats up a tiny bit. So that mechanical energy is converted into thermal energy. Now, that's almost all of it. One of the things you may notice is every time you drop something, you hear a sound. Well, that's because when you drop it, it hits the ground. It also sends a sound wave out through the air. That sound wave is carrying energy. So, most of the time, most of the energy is turned into thermal energy. Sometimes, well, you usually get a little bit of sound. Sometimes you may even get a little bit of light. Sometimes you drop something that, depending on the surface, there could even be a spark. So the energy is not destroyed. However, the mechanical energy is lost at this point. But the entire time that it's falling, we have conservation of mechanical energy. At the halfway point, half the energy was potential, half the energy was kinetic. We get the same thing whether we drop it and it falls freely, or even if we were to roll it down a ramp, or swing a pendulum. Let's do a pendulum for a minute. We have a pendulum. That's basically a mass on the end of a string. If we pull it up here and we let go, all we do is we pull it up here. By pulling it up here, notice it's a little bit higher than it was. We've given it a small amount of gravitational potential energy. We don't give it any kinetic energy, though, if we let it fall from zero. So I'm holding it perfectly still, has no kinetic energy, but it has a maximum amount of gravitational potential energy. It's going to swing until it reaches here, and at this point, the gravitational potential energy has fallen back to zero relative to its initial height. So we're treating this like zero. However, the kinetic energy will be at its maximum value. All of the gravitational potential energy we had here has been converted to kinetic energy. Now, this is an object in motion. When an object's in motion, it tends to stay in motion. So it won't stop just because, oh, I'm out of gravitational potential energy. I've got kinetic energy. I'm going to keep right on going. I'm in motion. And it will swing all the way until it's back to its original height. At this point, the kinetic energy, it'll stop again. The kinetic will be zero. And this gravitational potential energy will equal the same thing it did here. It can't go any higher because it won't have enough energy to go any higher than its original height. However, in a perfect world, it also wouldn't go any lower. Now, in real life, we may have some friction, we may have some air resistance. It might not go quite as high, and then it'll come back. Okay? But think about it. When we pull it up here, we're giving it potential energy. When we let it go, that potential energy converts into kinetic, but then it goes right through this middle point. Sometimes this is called the equilibrium point, and keeps going right back until all of that kinetic has been converted to gravitational potential energy. That cycle can go on indefinitely. Let's talk about machines. There's lots of types of machines, and the whole purpose of a machine is to make our lives easier. Whether it's a dishwasher, a washing machine, your car, all kinds of machines make your life easier. But how? Machines actually don't reduce the amount of work that has to be done. A machine can't make a situation where you put 20 joules of energy into the machine, but you get 25 joules of work out of the machine. That'd be getting more in than you put out. That's absolutely defies the laws of physics. That's a violation of conservation of energy. The amount of energy you put into the machine hopefully would equal the amount of work that you get out. In reality, you don't even get all of it out because there's always some energy that's dissipated as heat. Think about the machines you know. They almost always feel warm. They almost always make noise. Well, that's using up energy when what you want to use energy for is to do the work. Even a light bulb. If you turn on a light bulb, the goal of a light bulb is to make light, and they do. But if you'll notice, they also get really hot. So a lot of the energy doesn't go into making light. It heats things up. Okay? So I want you to remember, machines make work easier, but they cannot reduce the amount of work. All right, so how do they make work easier? Well, they usually do one of two things. They either change the direction of the force or they reduce the amount of force that you need. If you remember, work equals force times distance. If we can use less force, which is often easier if you're not real strong, you will have to make up by going through a longer distance. Okay. Sometimes they just make work easier by reversing direction. Suppose that you have a big heavy box and you want to raise it up 1 meter. Well, if this box weighs 100 newtons or 1,000 newtons, you're going to need 1,000 newtons of force to raise it up. Well, that's a lot. However, if I have a pulley, better move my pulley over a little. If I have a pulley, I know that this is 1,000 newtons. So I'm going to have to pull up with 1,000 newtons. But if I put a pulley, I can pull down with 1,000 newtons instead. Why is it easier to pull down with 1,000 newtons than it is to push up with 1,000 newtons? Well, gravity is your friend. Most people weigh, golly, at least 700 newtons. You can use your own body weight and gravity to help you pull down. Your weight and gravity don't ever help you pick something up. So simply by changing the direction and trying to pull 1,000 newtons down is easier than trying to lift 1,000 newtons up. So that's one way they make work easier. Another way is by simply making where you can do less work. We talked about that when we looked at the ramp. Let's talk about it with a lever. A lever is just along like a board. And here's our fulcrum. What if I want to pick up a boulder, a box, whatever it is? I want to pick it up and raise it higher. Okay? If we think about it, when we rotate, I'm going to try to draw it in a before and after position. And my art may not be as good as the art in the book. This is a fairly short distance. This is a fairly long distance. If the amount of work I do here, I'm going to have to step on this board and I'm going to apply some force. This force times distance, that's the amount of work I'm doing here. That's my input work. Ideally, it should equal the output work. Well, here, let's say I'm going to use a relatively small force, but a relatively big distance. Fairly small force, fairly large distance. And that's going to allow me to pick up a big weight and move it a small distance. This is a small distance. Okay. So if I have a heavy weight, I can move it a small distance using a smaller force over a longer distance. This type of simple machine is a lever. However, if we go back, we've already looked at something like this. When we looked at it before, we looked at it using a ramp. If I'm going to raise something to a height, let's say we want to pick up 1,000 newtons, and I want to raise it to a height of 1 meter. The amount of work that's being accomplished, my output work, is force times distance. So work in equals work out. In this case, 1,000 Newton force for one distance is 1,000 joules. Okay. If I lift it straight up, I'm going to need 1,000 newtons of force. However, what if I use a ramp? And instead of lifting it straight up, I use a ramp that's 5 meters long. If I use a ramp that's 5 meters long, then my force times 5, my force times distance here, this was, let's just look at this, was 1,000 newtons times 1 meter. Well, this is 1,000. If I divide by 5, I see I only need a force of 200. A 200 Newton force acting over 5 meters will allow me to push this all the way up to the top. I will accomplish the same work that a 1,000 Newton force straight up would accomplish. Now, it's really important to remember, that's an ideal machine. In an ideal machine, the input work is exactly equal to the output work. In reality, most ramps would probably have a little friction. I would probably have to push a little harder than 200 newtons because of friction. What if I had to work 250 newtons? Well, if I did 250 newtons for 5 meters, I would have put in 1,250 joules of work, but I would have only gotten out 1,000 newtons of work accomplished. What happened to the rest? 1,250 joules of energy in, 1,000 joules of energy out. Well, that 250 joules was turned into heat by friction. Friction does a lot of work turning mechanical energy into heat. Well, what happens if we don't have an well, let's do one more thing before we talk about efficiency. Let's just go back and review this idea of the force times the distance in, that's our input, should equal the force times the distance out. That's our output. Think of what that means in terms of the mass. If I want to half the amount of force that I use, if I want to use half as much force, I'm going to have to double the distance, because this product still has to be F times D, has to be exactly equal to this. If I want to use 1/10 of the force, then I'm going to have to use 10 times the distance. So the way machines often allow us to make work easier is they allow us to use a smaller force over a longer distance. All right, that's an ideal machine. That's where input equals output. The reality is that's not usually the case. Most of the time we have to think about efficiency. And efficiency is the work output. That's the amount of work we accomplish divided by the work input. Let's suppose you have a machine and you realize that you accomplished 1,000 joules of work. But in order to accomplish that 1,000 joules of work, you actually inputted 1,250 joules. If you notice, the efficiency is always going to calculate to be a number that is less than 1. I know how to calculate. Here we go. So if I do 1,000 divided by 1,250, it comes out to be 0.8. Now, most of the time we don't calculate efficiency as a straight fraction, but we can. If we do, we just need to remember it's always less than 1. It's not possible for the output to be greater than the input. That violates the laws of physics or conservation of energy. Most of the time, however, we want to make this a percent. So if I want to get percent efficiency, I'm going to take my fraction here and I'm going to multiply by 100%. Well, if I multiply this by 100%, I get 80%. So that's how we calculate efficiency. The higher this number, the closer it is to 100, the less energy is being wasted. If you're 80% efficient, that means 20% of the input energy was wasted. Usually it's turned into heat. Now, thermal energy is really valid energy. It's just not usually as practical to use. So it's kind of not what we consider useful energy, even though it's energy. All right, so let's think about where the energy on this planet comes from. There's actually a few sources. But almost all of the energy on planet Earth comes from the sun. As far away from the sun as we are, the sun's energy warms our planet. That solar heat, I mean, of course you think, well, that's responsible for solar energy misuse, but what does that have to do with electricity? What does that have to do with gasoline? Well, in fact, all of that usually comes from solar energy. Let's think about it. The sun's heat allows grass to grow. The plants take that energy, and by photosynthesis, they store energy within the plant. Then, a long time ago, dinosaurs ate the grasses and the plants, or dinosaurs ate small animals that had already eaten the energy in the grasses and the plants. And those dinosaurs grew to be great big creatures. And then they died. And then many of them turned into fossil fuels like coal or oil. That fossil fuels came from previously living organisms. Those previously living organisms got their energy from the food they ate, which got their energy from the sun. So every bit of energy in gasoline originated with the sun. Wind energy doesn't seem like that's solar, but wind energy is actually caused by differences in temperatures at different layers of the atmosphere. So that's also solar energy. Almost all the energy that you think of is really solar energy. It comes from the sun originally. Now, there is one major exception, and that's nuclear energy. Nuclear energy is energy that's stored inside the nucleus of atoms. Nuclear energy is the most concentrated form of energy that we know of. I can't even, I could look and I have numbers here. See what I have to say about that. Don't have numbers here. But I do know we are concerned with the use of nuclear energy mainly because of the radioactive waste that it generates. Until we have a way to deal with safety and disposal of waste, I don't know that nuclear energy will be popular. But if we ever solve those problems, nuclear energy could fuel our world for a long time. It does not create air pollution like other forms like fossil fuels do, so it has a lot of advantages. There's also some energy that's as a result of tides because of the spinning of our planet and a few other sources, but the majority of the energy on this planet originated with the sun, which is basically a gigantic nuclear reactor. That's what that star is. It's under a constant state of what we call nuclear fusion, and it gives off tremendous amounts of energy. All right, I think that concludes chapter 7. As always, if you have questions, please email me. I'm always happy to help.